In this lesson, we're going to be looking in more detail at graphing exponential functions and then how they could be transformed. Now, unlike quadratics and all of that, there's a different parent function depending on the base of the exponential. So if we look at this first example, this is considered a parent function. The parent function is 1/2 to the x. Now the other one is a transformation from the parent function. So let's start by looking at that parent function 1/2 to the x. Let's make a table. Let's go from -2 to +2. Now, if you have your calculator handy, you could put 1/2 to the x in your y equals and make a table that way. I'm going to do it by hand. Now, remember, if there's nothing on the outside of that parentheses, it's like having a 1 times 1/2 to the x. So my initial value when x is 0 is 1. And I'm multiplying by 1/2 each time. So when x is 1, I'd be at 1/2. Multiply by 1/2, and we're at 1/4. Now going backwards, the opposite of multiplying by 1/2 would be multiplying by 2. So when x is -1, we have a 2. And when x is -2, we have a 4. So let's plot our points. -2 goes to 4. Oops. -1 went to 2. 0 went to 1. 1 went to 1/2, and so forth. And we end up getting this decreasing graph because we have a decay. Let's also remember that we have a horizontal asymptote at y equals 0. Now let's look at what happens when we transform it by multiplying by 4 on the outside. If you remember from some of our other transformations, that is considered a vertical stretch by 4. Having a vertical stretch by 4 really means we're going to take each of those y values and multiply by 4. Try it in your calculator. Type in instead in your y equals 4 times 1/2 to the x. And notice what happens to our y values. The original was a 4. Now we have 4 times 4, which is 16. Original was a 2. Now we're going to have an 8. Original was a 1. Now we're going to have a 4. Original was 1/2. Now we're going to be at 2. Original was 1/4. Now we're at a 1. So let's plot those points. Well, I can't get to the 16, but I know it's way up there. When x is 0, we're at 4. When x is 1, we're at 2. When x is 2, we're at 1. The graph is still a decreasing graph, but notice it's just stretched up a little bit higher. Also notice that my horizontal asymptote is still y equals 0. Let's look at this next one. Again, we have our parent function here. That's the basic version, 3 to the x. So let's make a table. Our next parent function is 2 to the x. So let's make a table. 2 to the x. I'm going to still go -1, -2, -1, 0, 1. I'm even going to go all the way to 3 on this one. The initial value would be a 1. Times 2, we get a 2. Times 2, we get a 4. Times 2, we get an 8. Remember, that's also because 2 cubed is 8, 2 squared is 4, and so forth. Going backwards, I'd get 1/2 and 1/4. So let's plot our points. -2 is at 1/4, -1 is at 1/2, 0 goes to 1, 1 goes to 2, 2 goes to 4, 3 goes to 8. So we get this increasing graph with a horizontal asymptote still at y equals 0. Now let's take a look at this transformed function, 2 to the x minus 3. Take a moment and put both of these in your graphing calculator. Put 2 to the x in y1 and put 2 to the x minus 3 in y2 and see what happens with the graph. Make sure that the x minus 3 is all in the exponent. You should see that this is a horizontal shift right 3 steps. So literally every single point is moving to the right 3 steps. If you look at your graph, you should notice the shape didn't change. It's not vertically stretched or shrunk. It's the same shape, just shifted to the right. Also, the horizontal asymptote has not changed. It's still y equals 0. Now let's investigate what changes when instead of adding or subtracting with the x, we do it at the end. So let's start with that parent function, 1/3 to the x. So you're welcome to put it in the calculator if you need to, but my initial value is going to be a 1. 1/3 to the first power would be 1/3. 1/3 squared would be 1/9. Going backwards, when x is -1, I actually get a 3. And when x is -2, I get a 9. So that would be way up there. And notice we do get a decreasing graph. Horizontal asymptote is still at y equals 0. Now put the second one in y2 and see what happens to your graph. You should notice that it moves down 2 steps. So every single point is going down 2 steps. Notice what else shifts down 2 steps. Whoops. My horizontal asymptote also shifts down 2 steps. This is the only time our horizontal asymptote has changed. Vertical stretches and shrinks did not change it. Moving to the right didn't change it, so moving to the left wouldn't either. Even a reflection doesn't change the horizontal asymptote. What does is shifting the graph up or down. On this one, we're going to go into a little bit more detail. On each function, we're not only going to sketch the graph and talk about the asymptotes, but we're also going to talk about domain and range. So let's take a look. What would be the parent graph of this function? Well, the parent would be the simplest version, nothing being multiplied or added or any of that. So we would start with just 3 to the x. That would be our parent graph. Make a table. When x is 0, we're at 1. When x is 1, we're at 3. When x is 2, we're at 9. Going backwards, I would get 1/3 and 1/9. Here's the parent graph. So let's review domain, range, and where our horizontal asymptote is. The domain for any exponential function is all real numbers, or -infinity to infinity. The range is going from 0 to infinity. Remember, it never really reaches 0 because that's where our horizontal asymptote is. Let's talk through what the new one is going to do. The x plus 4 is going to move me left 4. The plus 1 at the end is going to move me up 1 step. So each point is going to go left 4. So I'm starting here, 1, 2, 3, 4, and up 1. Left 4, 1, 2, 3, 4, and up 1. Even that one, but that would be off the screen. What else is going to be shifted up 1? Well, that would be our horizontal asymptote. Here's my new graph. The domain is still all real numbers, -infinity to infinity. The range, now it has a boundary line at 1, so it starts at 1 and goes to infinity. That horizontal asymptote changes because we shifted up, so it also changed our range. Next example, what would be the parent graph, the simplest version of this function? Well, that would be 1/3 to the x. Make a table, or use the table in your calculator. -2, -1, 0, 1, 2. When x is 0, I'm at 1. When x is 1, I'm at 1/3. When x is 2, I'm at 1/9. Going backwards, I would get 3 and 9. So when x is -2, I'm at 9. When x is -1, I'm at 3. X is 0, I'm at 1. X is 1, I'm at 1/3. So I get my nice decreasing parent exponential function. The domain is going to be -infinity to infinity. The range is 0 to infinity. And the horizontal asymptote is y equals 0. Now let's talk about everything that's going to change on our new one. That 2 in front, that's going to be a vertical stretch by 2. In other words, all the y values are going to be doubled. I also have the -4. That means my graph is going to go down 4. So what else shifts down 4? Well, the whole graph, including that horizontal asymptote. So if I took half of my y values and moved them down 4, I'm going to take half of 9, that'd be 4.5, down 4. So here's 4.5, 1, 2, 3, 4. And you're welcome to use your calculator to make your table. I'm doing this by hand. Half of 3 would be 1.5. Oh, What did I do a half? It should have been doubled. So this would have been 18 and then down 4, which wouldn't have been there. This should have been 6 and then down 4, which would have put me at a 2. 1 doubled would be a 2, down 4 would put me at negative 2. 1/2 or 1/3 doubled would have been 2/3, down 4 would have put me about here. So I'd end up with my graph doing this. I cannot believe I messed up there. Hopefully you caught it. My domain is still negative infinity to infinity. My range has shifted because my graph shifted down. That boundary line is now at negative 4, and the graph keeps going up to infinity. My horizontal asymptote is y equals negative 4. What about this graph? What would be the parent graph? Well, the parent is the simplest version. That would be 4 to the x. The initial value when x is 0 would be 1. 4 to the first power is 4, and that'd be up to 16. Negative 1 would be 1/4. Negative 2 would be 1/16. That's too small to even graph. So I'd get a graph that looks something like this. Very steep because of that 4 to the x. My domain is negative infinity to infinity still. My range on any parent graph is going to be 0 to infinity because my horizontal asymptote is y equals 0. Now let's take and break down this new one. The 1/2. Maybe I was thinking ahead on that last example. This is a vertical shrink by 1/2. So on this one, I'm taking half of all the y values. I must have been thinking ahead. The x minus 4 is going to move me right 4, and the negative 2 at the end is going to move me down 2. So let's take each point. I'm going to actually start with that 16 down there. If I took half of that, I'd be an 8. So when x is 2, that'd be an 8. But I'm going to move it right 4. 1, 2, 3, 4, and down 2. When x is 1, I was originally at a 4. Half of that would be a 2. But I'm going to go right 1, 2, 3, 4, and down 2. When x was 0, we were at a 1. Half of that would be a 1. 1, 2, 3, 4, and down 1, 2. Remember what also shifts? It's that horizontal asymptote. Now you could have also found those points by looking in the calculator at your table. The domain is still negative infinity to infinity. And the range, because our boundary line has shifted down, is negative 2 to infinity. That boundary line is our horizontal asymptote at y equals negative 2. Let's do the parent function on this one together. F of x equals, and if we look at this one, the simplest version would be 2 to the x. And we've done this one already. Negative 2, negative 1, 0. I'll even go up to third. 2 cubed is 8. 2 squared is 4. And we can plot our points for our parent function. The domain is still negative infinity to infinity. The range of the parent graph is 0 to infinity. And our horizontal asymptote is still at y equals 0. Try to make a guess of what all you think is going to happen on this one. And this might be one that you really would like to use your calculator to help you when you start graphing so that you have good points. The negative in front is a reflection over the x-axis. It's also going to make all my y values negative. The 3 is a vertical stretch by 3. X minus 6 means I'm going to move right 6. And the plus 5 means we're going to move up 5. So I'm going to go ahead and put in that horizontal asymptote at 5 because I know it got shifted up 5 as well. So take a look in your calculator for a second. And see what you see as far as where the points are. Using the table in your calculator, you should be able to see that the very first good point is when x is 4, I'm at negative 7. When x is 5, we are at negative 1. Notice that it's really stretched. When x is 6, we're at negative 2. When x is 7, we're at 3.5. And we get a graph that looks something like this. The domain. Well, the domain is still all real numbers. The range has definitely changed. Our boundary is 5, but we're below it, so it's everything less than 5. That means negative infinity to 5. The horizontal asymptote is that boundary line, y equals 5. Now we'll be going on to the next section, but I want you to take a quick look at the example problems because this is the type of questions you'll be asked on your next quiz. You'll be asked to name the parent graph. You're going to be asked to give the domain and range and the asymptotes of the new graph as long as describing those transformations. Now, all of these transformations hold true for any base. So we're going to look at a very, very different base. In this one, we're looking at a graph that's f of x equals e to the x. E is called the natural base. Now we're not going to go into everything of where e comes from right now, but I want you to get the idea of the fact that it transforms just like all the other ones. Let's make a quick table so that we can graph this parent graph and then talk about all the transformations. So in your calculator, look for where you see E. One place you would see it is above the LN button, which I believe is to the left of the number 4. It'd be second LN. What that would pull up is E to the, and it leaves a little space. So if you go into your Y equals, let's put in E to the X and make a quick table so that we can do these quick transformations. In the table, you'll find that E to the 0 is 1. E to the first power is 2.718. And it actually goes on forever because it is an irrational constant, kind of like pi. It is used a lot in pre-calculus and in some of your science classes. Next one is 20.086. The main ones we're going to be looking at are these. Now, if you look at the graph in your calculator, you'll notice that it's an increasing graph with a horizontal asymptote at 0. So using that table to sketch our new parent graph, the parent graph I'm going to put in red. When x is 0, we're at 1. When x was 1, we're at like 2.7. When x was 2, we're at like 7 something. So here would be our parent graph. And we're going to be doing kind of quick sketches and using your calculator to plot points, but they're not good points. They're kind of ugly points. The domain of this exponential function e to the x is negative infinity to infinity. The range is still 0 to infinity. Its horizontal asymptote is still y equals 0. It's just like any other exponential function. It's just weird numbers. Let's think about what's going to happen on this next graph. On this next graph, you're going to have negative 1/2 times e to the x. What do you think is going to happen to it? So it's a good idea to leave this one in y1 sometimes and put this one in y2 so you can compare the difference. The negative is going to reflect over the x-axis, and the 1/2 is going to be a vertical shrink by 1/2. So if I take half and make it negative, I'm going to be about here. Half of that number, make it negative, it's going to be about here. And when x is 2, it's going to be down here. So we get the shape of our graph. The domain is still going to be negative infinity to infinity. The range on this one, since we're below the x-axis, is negative infinity to 0. My horizontal asymptote did not change because we did not transform up or down. On the next graph, parent function is going to look something like this. Our domain of the parent function is negative infinity to infinity. The range of the parent graph is going to be 0 to infinity with a horizontal asymptote at y equals 0. Same as always. What all is happening to this graph? Well, the x minus 4 is going to move me right 4. The plus 1 at the end is going to move me up 1. Now, just like our other trying to do one fancy way. Just like our other graphs, that's also going to shift my horizontal asymptote up 1. My points are going to go right 4 and up 1. Right 4 and up 1. My domain of the new function is still negative infinity to infinity. The range, however, has shifted because my boundary line has shifted. It's 1 to infinity. The horizontal asymptote is at y equals 1. Let's look at a couple more examples. Parent function. Again, we're still looking at e to the x. Zoom in a little bit here. E to the x starts at 1. This is like 2.7. Whoops. 2.7, and this one's like 7 point something. It looks something like this. Again, my domain is negative infinity to infinity. My range is going to be 0 to infinity with a horizontal asymptote at y equals 0. My new one, what all is going to happen to it? Well, the 2 is going to be a vertical stretch by 2. And the minus 5 is going to move it down 5. That's also going to move my horizontal asymptote down 5. So notice I put a little dashed line there to help me. So if I double my y values and move them down 5, this is going to move here. And when x is 1, we're about half. It's going to look something like this. The main things we're trying to get out of this unit are what the transformations are, what happens to the domain, range, and horizontal asymptote. The domain stays the same. The range shifts because our boundary shifted down 5. That boundary line is called our horizontal asymptote, and it's y equals negative 5. Last example. Parent function. 1, 2 and a little bit, 7 and a little bit. Here's my parent function. The domain of the parent is negative infinity to infinity. The range of the parent is 0 to infinity. The horizontal asymptote is y equals 0. Now think of everything that's going to happen on this one. If possible, pause the video so you can write in what you think all the transformations are going to be before you ever look at it in the calculator. The 1/2 is going to be a vertical shrink by 1/2. The x minus 4 moves me right 4. The minus 2 at the end moves me down 2, so that moves that horizontal asymptote down 2 steps. So when I plot my points, and I'm going off of my calculator as well, I notice this one gets big really, really fast because all of this is really close to that boundary. The domain of my transform function is still negative infinity to infinity. The range has changed because we shifted down 2. the horizontal asymptote is that boundary line, y equals -2. Be prepared to discuss the transformations, domain, range, horizontal asymptote, of any exponential. It doesn't matter what the base is.